Hello, everyone. Welcome. Oh, I'm quite to the side today. I need to move this and not break it. Unfortunately, the way that my monitor is positioned doesn't point at me. Hello. I'm assuming those caps lock were unintentional, but I'm gonna take it like enthusiasm. Sujan, I am so glad to see you. Welcome. Let me see if I can point this down a little bit. My webcam has this universal mount thing, and it's a little sketchy. It doesn't necessarily stay in one place very well. Oh well. Hello, everyone. Welcome back to another exciting episode of Managed 368. What's up? Most people don't call me by my last name, mostly because my last name just isn't that fun to say. I played on a high school tennis team, which, while that is not much of a sport, it is a sport. I know that might be hard to believe that it's, in fact, a sport. A little congested. It's spring in East Tennessee, so lots of pollen and allergies from my pets because I'm allergic to my pets. But about last names is no one was like, "Hey, Cook, what's up?" It's just not a fun name. Might as well just say Rob. But we had Wozek. Hey, what's up, Wozek? Yeah, that's better than Adam, right? We had Anderson, John Anderson, Russell Graves. Everyone call him Graves. Just Cook. Such a lame last name. Yeah, I've heard actually. I heard about the big pile up this morning. Scary. And I'm kind of surprised, I guess, because it was, normally the roads are quickly safe, so it's really scary that it still happens, Hello, Mo. Welcome. Okay, we will come back to this. There's something I want to show you on here, but I will put it at the end. Well, it's kind of halfway through the announcement, so maybe I should have done it then, but I didn't. All right. Come on. Keep on keeping on. Okay. So, reminder about the University Climate Study Survey. Still active for the next 2 weeks, coming through Monday. Okay, so the real thing that's new today, other things, the rest of the things pretty much aren't anything new on here. There is one major new thing, and that is the MindTap access. I imagine that several, if not most of you, have had your 14-day trials expire. So if your trial has expired on MindTap and you try to do your homework, which is due Sunday, as I'll say in a moment, it won't work. You will not have access any longer. So I contacted our Cengage rep, Lindsay, and she provided a PDF, which seems to me to be a little sparse on instructions, but hopefully this is enough. So I put this link here. In case you didn't see where that was, let me go back. Okay, so pretty much everything that I'm putting up these days is on links to online learning resources. Yes, and I did it again, trial version, it works. Awesome, good. I'm glad to see that it worked for you. So everyone, here's where it is. This is where you go to find it. Links to online learning resources is right at the top, and you followed along. That's okay, Sujan, no rush. You got through Sunday. So you go to your homepage, and there's a button on the side that says Start Trial. And then Explore Cengage Unlimited, you should be able to go back. No, you don't need to do it again. Just the once is fine. It's one big survey. It's just been open for a while because, of course, everyone's, got coronavirus stuff to worry about. So this is it. There are supposedly only 3 steps, so hopefully that will be clear. Sujan said it worked for him, so hopefully that's a smooth process for the rest of you. Okay, so slide update. So as you know, we already skipped some stuff from Chapter 7. We have a little bit left for Chapter 7 that we'll talk about here in a minute. We have Chapter 8 coming up. We'll start Chapter 8. We'll get through a handful of slides, not too far today, I wouldn't expect. Got through, I think, like 11 slides in the previous lecture today. But when we come to it at the end of Chapter 8, we will skip population proportion. So at this point, it looks like we'll spend most of Monday on Chapter 8, and then we'll finish up on, we'll pick up Chapter 9 and do that on Wednesday. So just some upcoming assignments. So we have the Chapter 7 Mind Tap homework assignment. I published that this afternoon. My water's over there. Our Mind Tap assignment this afternoon. That is due Sunday at midnight. I mentioned this on Monday, I'm pretty sure, but I had some people complain about not having until the time of class, and then people forgot about the vocab quiz last time this happened. Maybe not in your class, and then people got upset about, oh man, I wish I hadn't forgotten about the vocab quiz. So I'm going back to my original instinct, which is homework due at midnight, and then we'll have the vocab quiz on Monday. So that gives you the day of Monday to work on your vocabulary words if you haven't already. Now, I posted the list of Chapter 7 vocabulary words to D2L a while ago. Hopefully you saw and looked at those, because we've got a vocab quiz here in a few minutes. I cut down some of the words that we didn't cover. Left it with a handful of words. I forget, 16 or something left over. Next week, on Monday and Wednesday, respectively, we'll do Chapters 8 and 9 vocabulary quizzes. Those are both short. There are 9 and 10 words, respectively. So they're both short lists, so hopefully they'll be easy for you to memorize and knock out on the quiz. And I can tell you that students did very well on the vocab quiz today, so hopefully that will continue to be the case for you guys. Now, I had told you before that we'll have at least one quiz and one in-class assignment. I don't have anything else to announce on that. I am going to keep trucking along with that. Is the week on the 20th. Yes. This coming Monday. Oh no, isn't that crazy? April 20th is next week. That's next Monday. It's not even like the end of the week. April 20th is next Monday. So, the last day of class is April 27th. We are barreling into the end of the semester. Yes, Ben, you're right. And since you've brought it up, I will tell you that we had a course that was, and my undergraduate, we had one of our courses. So at Alabama, we used freshman year courses are 100 level, sophomore year courses are 200 level, third level, 300 level, and 400 level were each, one additional year. Because there were a lot of structured programs that had like first year, second year, third year, fourth year classes. And one of our 400 level classes was given course number 20, which meant that it was 420. And every time I said it, there would always be like one or two students in the back of the room like chuckle to each other. And so when I taught the class, I was like, all right, let's just all laugh it out on the first day. Yes, it's a number. It's the marijuana number. Ha ha ha. I made it really awkward. And then nobody laughed about it anymore, because they were like, oh, please don't make him laugh like that again. It was horrible. So I think it worked. So I'll probably, I'm sure I'll remember. We'll see. If not, maybe I'll forget, but it is time. It's 4/20/20 too. I'm not sure if that makes it like extra weed number, but I feel like it should be. I saw a YouTube channel about people like retrospectively on 2020 so far, and they called it 2020 hindsight, and I was like, that's clever. I'll try to come up with that. Yeah, basically. Actually, what is the weed number squared? Okay, it's not actually the weed number squared, but it's close. I like that idea. Let's just not tell anybody that's the actual weed number squared. I like it. It's like 420 up 20. It kind of works. I like it. Okay. Let's see. What else? Anything else? No, that's the important stuff. All right. So, yeah, let's move on. All right, let's do it. Let's do that thing. There's a song by the Jeff Coffins Quartet called Better Do That Thing, or Better Do Your Thing. I think it's Better Do That Thing. I'm going to play it for you just so we can, while I pull the quiz up. See how fast I can find it because I'm running out of options. I don't care that much. All right, I didn't find it, but this is another track of his. Oh, I don't like this version. I want the other album. Oh well. This is the saxophonist from Dave Matthews Band, if you didn't know. Yeah, I don't like this recording, but I will. In fact, I'll listen to it. Oh, here it is. Better Do Your Thing. This is it. Alright. Okay. Hide from users. Unchecked. Users set correctly 15 minutes. And then it'll be prevented from making changes. Good. What time is it? 7:17. Perfect. Okay. Better do your thing. I'm going to mute my audio here, the desktop audio, so anyone who sends messages won't be dinging in the chat. Good luck. 15 minutes. we should be finishing up. Some of you may have timed out already. I don't know. There's 2 minutes left in the window, but depending on how long. You have 15 minutes from when you actually start it, so it depends on when you start it. Good. Glad to see it there. If I go by everything, I'll see what I mean. What do you mean? If I go look at your exam? Because I did when you asked me about reopening it. And you used the time. So, because like some people did the exam in a few minutes and turned it in. So if they said, if they felt like they didn't understand how the timing thing worked, then it's easier to give them more time than, because I don't imagine that you filled it out and then sat there for 10 minutes, right? Like it's. So, I don't want to be the bad guy. But you have only so much time to work. I mean, I told you had 30 minutes to work. Like, again, though, I did not want you to take your 30 minutes and chop it in half and say, I can only work 15 minutes on my first attempt. Like, you have 30 minutes to work. If you need 30 minutes to fill out one attempt, then that's what you should do. You don't, it sounds like, you're saying you wanted more time, then you cutting it in half and doing 2 attempts inside of 30 minutes would be even worse than doing it all in 30 minutes. So I don't think that you did something different from what I wanted you to do. Now the results may not have been what you wanted, but I don't think that the process was unfair to what other students had. So if I made that exception for you, I would have to make the exception for everyone. And the truth is that I gave a longer exam last semester, and I gave a longer exam in person. Now, it was in person, but I gave a longer exam, and you had half as much time. So I doubled the amount of time that you would have for this exam. So a full twice as long. So now, if you're upset about your grade, there's good news. Or disappointed. If you're disappointed in your score, you want to improve your score, you can. That is the entire function of the final exam. Like, that's the whole point of having a 4th exam where you can replace your lowest score. That's the entire function of it. So, so that's why we don't need to panic. We don't need to panic and, freak out right now, because there's still another opportunity for you to make this go completely away. The final exam, you do well on that, and any low score you have, any single low score will go away. Speaking of low score, actually, or speaking of single exam score, more accurately, I'm having a little bit of frustration with the D2L gradebook. It won't do what I wanted it to do, which is take a formula and just basically add the 5 exam pieces together and make a single score out of it. You can't do that. You can, but it won't go inside of a category. So you cannot have it automatically compute a exam 2 score and then consider that as one of the 3 to drop. So what I've done is, I can't remember if I did it on your section already. I was working on it on the other section, testing the gradebook. I think I did it for you guys. Let me see if it's in the gradebook this way. Yeah. So I've added a category, and I'll put it on manage, so I'm hiding everyone's individual scores, but you can kind of see here. So there is a exam 2 breakdown category that has the 5 exam 2 scores. Yes, Daisy, there's a practice exam for the final. It is practice exam for exam 1, practice exam for exam 2, practice exam for exam 3. That is your practice exam for the final. because they're all the same. It's just the 3 exams squished together. I will be taking out the question. I need to go back and look again. I don't think there is a right answer, so there's no way to reward someone who got it right because there isn't a right answer. But it is on my to-do list. I have a proposal that I have to look at before tomorrow, and then after that, I'm going to look at the erroneous question. And then I will be manually entering the exam scores together. By manually, I mean doing it in Excel, but I'm going to have to manually put together all of the these 5 exam scores and turn it into the exam 2 combined score, which is right here. So I've already made the category. It will go right here, but I have to type in the scores manually, which will be the sum of these 5. But you can see that it's out of 19 and not 20. So because there is a question you cannot get right, it will be graded out of 19 instead of out of 20. But yes, otherwise, yes. Ace, yes. It's divided by 19 because you're going to have missed the question unless you just got miraculously lucky and guessed the right answer to 4 decimal places, but that would 1 in 10,000. Yeah, not likely. Unless you've got a sail and a lot of rubber. Unless you've got a rudder and a lot of sails hidden in that bodice. Unlikely. Yes, so I will have to do it manually. I'll let you know. Okay. Let's get it on. In the words of... What is his name? Guy Ledouche, I think. From... what's that show called? It's an old, like, absolutely ridiculous Japanese game show. Kakashi's Castle, I think. It was absolutely ridiculous. I don't know what his name was in Japanese, or they called him Guy Ledouche in the American version. My mouse is hung up. By the way, if you keep seeing this, I have a little blanket. I'm chilly, so I've got a little blanket going on. So I'm tucked in. Okay, so here's chapter 7. This is what we're going to be finishing up. We're all the way down here on this last 6th and final bullet point, other sampling methods. So we're going to scroll all the way down to bullet 54. So, a 1, a 2, a skiddly-diddly-do. Sampling methods. So this whole thing, as a reminder, we are working on... I think there's a way to make that automatic, that when I change to PowerPoint, it automatically kicks over, so I can't forget, like I just did there. Anyway, so remember, this I've been using the metaphor of a pyramid, that we are starting out with the idea of data and samples, and from there we're computing point estimates. And then we're going to use point estimates to create statements, probabilistic statements about how close our information, how close our guess is to the truth. And then we'll use that to answer questions about populations. And so we started out we sort of skipped the step on sampling. We talked about it some. We talked about simple random samples specifically. But we didn't talk very much about anything else from sampling methods. We jumped up into point estimation. So we're going to end this chapter by kind of taking a step back to other sampling methods besides simply simple random samples. So there are five we're talking about today? Yeah. 5 sampling methods: stratified random sampling, cluster sampling, systematic sampling, convenience sampling, and judgment sampling, one of which was on your vocab quiz a moment ago. So, stratified random sampling, the population is divided into groups of elements called strata. Stratified is a word that exists outside of statistics, and it just means like separated, So we have separate chunks of elements. It's important that each element in the population, so again, these like people or items or whatever we're talking about, must belong to one and only one group. So each individual is put in exactly one item. And the best results are obtained when the elements within each group are as much alike as possible. We call this a homogeneous group. So homogeneous means everything in the group is the same, very similar to each other. Homogeneous, you may have heard this word. Or as opposed to a heterogeneous group where everything is as different as possible. So in this case, we really want the groups to be homogeneous because what we're going to do is take a simple random sample from each stratum and then combine the stratum sample results into one parameter estimate. So the idea here is that if we do a good job of breaking our strata into homogeneous chunks, so there's not a lot of confusion between the different groups, then this method is as precise, as good of a job as simple random sampling, but with a smaller total sample size. So you have to do the work up front of making the strata, and they have to be good strata, but then the rest of your analysis is easier because you've got a smaller sample size. So that's really good. Of course, if you don't have good strata, then you will have less good results than you would have had before. So generally, this is used when we already have some obvious key characteristic like department, location, age, industry type, something that's like a really obvious demographic. Maybe I'll use class standing. Do you have at least 60 hours? Okay, that's one group. Do you have at least 90 hours? So I guess it'd be 60 to 90 maybe. And then if you have 90 hours or more, then you're in that group. Whereas 60 to 90 is a group, 30 to 60 hours is a group, 0 to 30 hours is a group. Or maybe you would chunk things by like transfer students and non-transfer students or whatever. Like you can have all these different groups. Now you wouldn't use transfer students, non-transfers, and the different standings because you'd have overlap. You'd have students that are both transfer students and have, junior standing or something like that. So again, you can only have one stratum for each individual. Generally you want to do this when you've got a pretty good idea of at least some characteristics of your population ahead of time. So some way of identifying them. Now, a similar but sort of opposite approach is called cluster sampling, which is, again, we're dividing our population into groups, not strata this time, we're calling them clusters. And the idea here is that we're making representative, small-scale versions of the population. So these are heterogeneous groups. It's basically a little microcosm. It's the population, but small. And then, rather than taking samples from the clusters, we sample the clusters, meaning let's say we had 100 clusters that we made, and then we would take 10 of those clusters and include everything in the clusters. So that's it. Okay, but if you can really do that effectively, if you can say like, okay, these people together are representative of the population, these people are representative of the population, then you probably know enough about the population that you don't really need to take a sample anyway. Like if you have that much understanding of your population, you probably know the averages of these, the population mean or the population standard deviation. You probably already know these. So it's not usually that simple. Rather, what we do is we use something that's an existing boundary, like area sampling. So, city blocks or some other kind of well-defined area. And then we take a sample from those clusters. In fact, this is kind of how voting works. You group together like the different states, and then the different states have their different, everyone votes within the state, and then you clump all the results by the state. And actually, it's clumped not just by states, but by voting districts. Now, here's the problem. Gerrymandering, which is this process where the government restructures the voting districts, is done very much intentionally to mislead voting. It is done to be the opposite of good clusters. That it's literally done to skew the data towards whichever party is in charge. And I don't know how it's not illegal. Like, it doesn't make any sense to me at all that it's permitted, because it is such a scam. But Here we are. So in that instance, in the case where we have gerrymandering, you don't want to use voting districts to as clusters, because we know for sure that they're not representative. They're not microcosms of the population. Okay, so I've kind of talked about some negatives. What's the advantage? Well, it might be that gathering sample data of people is so expensive. It's really, really expensive. So having close proximity of elements, one block, for example, can really save you a lot of money. And so you can end up getting a lot more data at the same cost than you would have been able to get. So even though you generally require more data than you would for even a regular simple random sample, you can usually get it so much cheaper that it might be worth it. That you can get more for less, basically. And when less is more, or when more is less, it can work out for you. So there are times when this makes sense. Systematic sampling is the simplest of all of them, even though it seems probably the most complicated, other than just simple sampling. Systematic sampling says that you have some desired sample size, like 100 or something, from some population of a specified number, some specified size, like capital N. So let's say we want a sample size of 100 out of a population of, I don't know, like 1 million or something. I'm making up numbers. So our sample size of 100, use my little pen here, of 100, population size of 1 million. 1, 2, 3, 4, 5, 6. Okay. 100 over 1 million. So N is 100, capital N is 1 million, and we have a formula, N over capital N. 100 over 1 million. In this case, that is 1,000, right? 100 divided by 1 million is 1,000. So what that would say is, if I'm going to systematically sample a sample size of 100 from a population of 1 million, then I need to sample one element every 1,000 elements. So rather than just arbitrarily break them into groups of 1,000 and then consistently, and then just like sample each 1,000 randomly, instead we pick the first number randomly, like, I don't know, 73. We pick some number within 1 in 1,000, and then we just go exactly every 1,000. So we would do 73, 1,073, 2,073, 3,073, and you just take every 1,000th individual element until you run out of data. So it's really simple. You just the sample size over the population, and then every that many take one, and then this works well when you have a like population list, if that list is a random ordering. If you do like, let's say, alphabetical, that may not be very good because you're going to have spikes. You're going to have groupings in the language from cultural tendencies in spelling. So certain cultures have tendencies, leanings towards certain letters, and so if you sample by alphabetical, then you may miss an entire cultural group because you just skip it. Whereas if you sample randomly, you have in some ways a better chance of getting it. But anyway, it's not the end of the world. It's not a horribly. It should be a small bias in that regard. So the advantage of this is just generally easier to do. Requires less like brain power, less computing power. But it also may not necessarily be better than a simple random sample. So I gave you an example. A more specific example might be selecting every 100th listing in a telephone book or something. And then that's more random because it's going to be broken up by, you could do individuals, but it also could be broken up by, like neighborhood or something. And then every 100th would kind of jump around. So it might work out. All right. And then so those three are probabilistic techniques. We're using probability. We're using numbers and math theory to pick our sampled elements. But the last two, we're not going to do that. So starting with this one, convenience sampling is non-probabilistic. Items are included in the sample without having any probability of them being selected. They're not saying like, oh, we take this one or don't take that one. The sample is identified by convenience. And in fact, I've given you examples of this several times, and this is like a professor conducting research using student volunteers. It's the people who are around him, not necessarily him, her, whatever gender, whatever around the professor that is most convenient. So there's no guarantee at all that those students are representative of the population, that it is a good sample. It just happens to be easy. So advantage, it's easy. That's pretty much the end of the advantages list. Disadvantage, it's impossible to know how good your sample is, and therefore it's impossible to know how representative of the population the sample is. Very flawed. Judgment sampling is actually better usually than that, although it's still not better than a probabilistic method, but at least I think it's better than convenience sampling, which is that you ask an expert, which hits hard right now in our in our political system. It's like, how about we ask an expert's opinion and then actually use it? Wouldn't that be wild? Just an observation, just something to try. Certainly, we haven't tried that in a while, so maybe we should. Just saying. Speaking of, judgment sampling is taking some person who is most knowledgeable on a subject, and then we just ask them, hey, would you please identify elements of the population that he, she, whatever, feels are most representative of the population? So it is non-probabilistic, like a reporter. So this is actually pretty common. I understand that this happens a lot in reporting, that usually you'll find reporters, some reporters anyway, are very specialized. You'll see like, oh, this is a sports journalist, this is a whatever. Well, some like political reporters will do specific types of cases, like, oh, I only work on excuse me I only work on new bills supported to Congress. New bills submitted. There's the word, submitted to Congress, that deal with human trafficking or something. Like, they have a very specific expertise, so asking them like, hey, who should we talk to if we want to get an impression of what the Senate is going to vote regarding some bill? Then they would have a really good idea of, oh, well, votes tend to follow these four people, either intentionally following, like, okay, we asked him yesterday what he was going to vote, and so for the sake of, having partisan voting, we'll all follow this one leader. Like the leader of a party will sometimes, it's like partisan voting, which really irritates me. I hate the political party system. Really has some downsides. So in that case, you don't even need 4 experts, 4 senators. You need 2. And then, great, we know how everybody's going to vote because it's partisan. And so there's no democracy going on at all. Yay. But then, 3 or 4 out of 100 is, reasonable. How about a no-party system? Wouldn't that be wild? You just have to vote for somebody. You just got to throw it out there. You just got to... Wait, hold on. I need to zoom in on this one. You'd have to have an opinion. You'd have to think for yourself. You'd have to think for yourself. I know. Okay, let's just go to a new topic. Thinking for yourself is too scary. I can't talk about it. No. Stay sheep, everybody. It's way easier. Okay, why judgment? Well, it's easy. Hey, Bob, what should you do? Okay, do this. All right. Disadvantage. Quality of the sample results depends entirely on the judgment of the person selecting the sample. So, if you actually get an expert, great. If you get someone who is not an expert. Or, yeah, I mean, experts are wrong. Like, it happens, right? That's judgment. Judgment is not perfect. It's not infallible, So sometimes sometimes they'll guess wrong. Especially when sometimes that you're taking a gamble. Like, I don't know. But if I had to guess, I'd say 30% chance that it's this or something. Those are not good odds. 30% chance is not good odds. So, it might work out. It might not. So generally speaking, general recommendations, use probabilistic methods, avoid non-probabilistic. And the reason is we have formulas that can actually evaluate how close our sample results are to the population parameters that we're estimating, which is actually what we're going to do in the next 2 chapters. And we cannot use convenience or judgment samples in these methods because we have absolutely no idea if they're connected to the actual population at all. So that's where we're going to go. Is we're going to start evaluating goodness of our results, and that's chapter 8. So we're going to go straight into that with just that as a transition. Okay. So chapter 7, all wrapped up. That's chapter 7 again. Just the one was fine. Thank you. We don't need to do it again. And now chapter 8. Okay. It is really amazing to me how much darker my face over here is when I don't have the monitor shining white light. Which you can see the reflection over my shoulder, by the way, as I move the image around. Oh, well. I need to get one of those, like, softy glow lights. I tried my phone last time. I think that was in this class maybe. Turned my phone flashlight on, and it was just like dazzling. It was like it's literally a flashlight shining in my eyeball. So yeah, it illuminated my face, but it was very distracting. Okay. Chapter 8. Okay, so chapter 8 is there's very few concepts that we're going to discuss. However, they are a little bit complicated, so it will take us a little while to go through it. We have the population mean interval estimation. So, you've probably not heard the phrase interval estimation outside of this class, but you have heard of estimated intervals. So you have heard things like we believe that the number of cases of new COVID cases this month will be 10,000 plus or minus 100 or something, right? You hear these kinds of statements where they give you an estimate and then they give you some amount of wiggle room side to side, where they say, might be more, might be less. We don't know exactly, but we think it's going to be in this kind of a range, but here's the number we're going with. Right? You've heard these before. And this is exactly what we're going to be doing in this chapter, is we're going to be building those estimates using statistical theory to specify how precise, how accurate we think we're being. So we're going to start out with the case where we know the population standard deviation, and then we'll move over to where if we don't know the population standard deviation, and then we'll work backwards a little bit on how to determine the sample size based on an acceptable level of risk. As before, we're going to skip the population proportion section of this. Speaking of as before, I didn't tell you. Hold on, let's rewind for a quick second. Okay, something I forgot to tell you. Reminder, 2 things. 1, MindTap homework. I think I might have said this part. MindTap homework, Sunday night at midnight. I said that, right? Okay, here's what I didn't say. Maybe I did. Can't remember. Did I say this? Chapter 8, Chapter 9 vocab quizzes next week. Did I say this? I don't remember saying it. But then maybe I do. I don't know. But I'm saying it now. Chapter 8, Chapter 9 vocab quizzes next week. Monday and Wednesday. Okay, I said it now for sure. Okay, I did. Good. All right. I just want to be sure. Okay. Glad to say it twice rather than 0. Okay, so if you really think that your estimate is perfect, you're going to have a rude awakening. Am I going to post them? No, because they're already they're on MindTap. There's only 9 words for chapter 8. There's 10 words for chapter 9. So all the words will be on the vocab quiz. So go learn the flashcards on MindTap. There's a flashcards button on the side. Choose chapter 8. Do it to it. That is a better way to learn than having it listed on a spreadsheet or on Word. Well, I mean, if you have the textbook, you can use those words there too. And they're in the glossary in the ebook as well. You've got lots of choices. They're all the same words. I promise. Okay, so basically, what are we doing? We're estimating. We're using chapter 7 ideas to make an interval estimate. To make a point estimate. We're making the point estimate, and then we're going to be adding or subtracting a margin of error. Okay, if you got any more questions, hold them to the end. Let's not get derailed. Okay, the purpose of an interval estimate is to provide information about how close our estimate is to the value of the parameter. I already said that. Okay, and I said before, you have point estimate plus or minus error. In the case of a population mean, then our point estimate has the symbol X bar, which we have on the screen. So X bar plus or minus the margin of error. It's the same idea. I've just plugged in the X bar to the point estimate. So we'll start out with the easy case, which is if we actually know the population standard deviation. And in case you're skeptical saying, how would I know the standard deviation if I don't know the mean? You'd be surprised. Actually, in a lot of terms, a lot of real-life processes, the standard deviation is fairly consistent, while the population mean may be dynamic. It may be less stable. And so you may have no idea what the current mean is, but you can use the old standard deviation and have a reasonable level of certainty that it's still practically close. It's close enough. So if we have access based on some reasonable level of history for the population standard deviation, that's the good case. Or if we don't have that, failing that, we will use the sample standard deviation. So, like I said, if we have a good estimate based on previous history, then we call this the sigma known case, because sigma is the population standard deviation. So this is the sigma known case. And that's where we're starting. So before we hop into the actual meat and bones, the theory of the of this chapter, I want to start out by kind of building some intuition, meaning building some brain waves, building some neural pathways, and so on. Okay, here's my brain teaser. If I were interested, so think back to chapter 6, by the way, normal distributions. So we talked about you plug in an X value, convert to a Z value, then look up the Z value on the probability table, and that gets your probability. We can go the other direction. We didn't talk about it much, but you put in a probability, use that to find a Z score, and then you convert from the Z score to an X value. That works, right? You can do that just fine. You can go in either direction. It's just algebraic ordering. Doesn't matter. Okay, so with that in mind, if I want to find the middle 95% of the data, so like this image I have here, this is of course 100% of the data of the values. So then how much is in the sides? So first of all, how much is in the sides? And then second of all, what probability is in specifically this tail over there? I'll give you a second to think about it, but put your answers in the chat. Let me see what you got while I get my water. Stay hydrated, folks. Voting from Dorothy. Anybody else? Okay. A couple more votes. Stunning. Okay. All right. Coming in. All right. Let me look, by the way. My dashboard's frozen. All right. I'm seeing 18 viewers, which is, by the way, slightly over half of our class, which is disconcerting. Probably why I keep getting angry emails. Not keep getting, but I've gotten a few angry emails about how bad communication is in the class. People don't come to class. That makes it hard for me to communicate with you. All right. 5 votes out of 18. Out of 18 people. Similarly uninspiring. All right. 6. We're a third of the way there. We made it a third of the way. That is half an F. We did it. All right. Yes. In case. Okay. So let's walk through it. If we have 100% of the data under the curve, and then we have 95% in this region, then what has to be left over? Well, we have 100% and 95%. So then whatever is not in this blue region has to be in the other, blue region. I'm going to call this dark blue. So if it's not in the blue, then it has to be in the dark blue. So, exactly, Mo. Yeah, it's 5% left over. But that's between this bit and this bit. And if you recall, then the normal distribution is symmetric. It's symmetrical. So what's on one side, if I draw a line on the middle, what's on one side is the same as what's on the other. And I did specify middle 95%, implying that this was over here and this over here are the same size. Therefore, as Ace has precisely said, 5% is the leftover divided by 2. Well, I can hold up 2 fingers. Divided by 2 to give us our 2 pieces. So it's not 25%. It's 2.5% actually. With the font on chat, it's kind of hard to tell the difference. I know some of you said 2.5%. Some of you may have said 25%. But again, it's hard to tell the difference. Maybe because the text isn't big enough. I can make the font larger, but of course it'll just explode over the picture pretty soon. So this is my compromise. Okay, so yes. Middle 95% is 1 minus 95%, 5% between the two sides, and then divided by 2 gives us 2.5% on each side. So the value that we look up is 0.025. And that means, by the way, I should be clear about this. When you look at the Z table, you know there's those Z's along the left and the top? Yes. 100 minus 95 divided by 2. 2.5. So we look up 0.025. So we look at the Z table afterwards. So you create the 2.5 bit, and then you're going to go to the Z table. And on the Z table, you're going to look up 0.025 in the middle of the Z table, and that will give you a particular Z value, which it turns out is a negative 1.96. Which the more you do these kinds of things, you'll just remember it eventually. 1.645 is the 95% cutoff when you're doing cumulative effective percentiles, and then I think it's 1.28 is 90%. Could be wrong. Okay, so the reason we did it this way, so we're building towards the formula that we're going to use, and so there's this idea of alpha over 2, which we did an over 2 a moment ago, right? We did 5 divided by 2. Where did that 5 come from? 1 minus a probability, right? So we said 95% is our probability, and so this right here, probability equals 0.95. And we're saying this probability is also equal to 1 minus alpha. Which, by the way, if you don't know, this is the lowercase alpha, Greek letter. So if my probability is 0.95 and my probability is also 1 minus alpha, then 0.95 equals 1 minus alpha. And therefore, alpha equals 0.05. Sorry, I ran out of room. That looks like a 6. Can I please have the thing? Okay. Whew. Okay, you're seeing this, right? I'm clicking on it? Okay, gracious. Please let me write on the edge. I can do it. Okay, 0.05. So alpha equals 0.05. So then we're going to use the formula z that's associated with alpha over 2 times the standard deviation of the sampling distribution, which is written like this. Z associated with alpha over 2 times the standard deviation of the sampling distribution. That's what this says. So if alpha is 0.05, then what is alpha over 2? It's 0.025, which is exactly the answer that we calculated in our brain teaser a moment ago. So we can take that same picture I had for you a moment ago, and we can plug in some new things. We have 1 minus alpha, so this is our 95%, right? That's this guy right here. This is all of the possible x bar values, x bar again being the sample mean. So all the possible sample means, 95% of them are in this region, are between z alpha over 2 times sigma x bar, mu minus all that, or mu plus all that will give us these two lines. And then there's alpha over 2 percentage over here, alpha over 2 percentage over there. And this is the sampling distribution of x. Most of it is right near mu, and there's some of it over to the sides, and then there's a very small percentage, 2.5% each on each corner. Okay, so hopefully that's starting to make sense. If not, we'll do an example here in a second. So this is just kind of going back to that brain teaser, wrapping it all together for your reference. And if you look up the probability that z is less than or equal to 0.025, you will find z of negative 1.96. So if you're not feeling confident on what that means, then we're running out of time in class. So I want to do one more slide before we cut out. But you can go take a look at the z-table and find negative 1.96. You'll see 0.025 associated with it, and you'll hopefully start to build this intuition. And of course, we're only on slide 10. So as we go, we'll do more examples. We'll help. It'll make more sense as we go along. Remember, we're not worried about Chapter 8 for this weekend. This weekend, you just have Chapter 7 homework, which, by the way, ACE should be posted. I'll go look at it in a second. But for now, again, so we have mu, we have an interval, which is being built plus or minus z alpha over 2 sigma x bar. So we're adding this amount to the right. That gives us this line over here. We're subtracting this amount, which goes to the left, which gives us this line over here. So this means that 95% of all samples that we could construct, so 95, if we made 100 samples, 95 of them would have a sample mean that would fall within this interval here. Would fall in this group. 5% of them would not. But remember, we don't know the population mean, and then we evaluate the samples to see if they're good. We don't know. We're just going to get a sample, and that will give us information about the mean. So I'm just letting you know that if we knew the mean, then we would be able to make this assessment of does it contain the mean or not. But we don't know. What really happens is we just get a sample mean, and we build an interval around it, which, by the way, is the same width as the one that I've described here, plus or minus z alpha over 2 sigma x bar. So maybe it's here. Maybe our x bar is actually here. And in which case, we're going to say, we would not know any of this up here. We just know this interval. That's our whole world. This interval is our whole world. And we would say the population average, the true population average, is probably somewhere between this point and this point. But we don't know where. And we're not saying that this is more likely than that. We have no idea. Sure, with this information, I can tell you that our estimate's too high, but we wouldn't know normally. And, the next time we take a sample, it might be even higher. And we would construct our new interval, and we would say, actually, we think it's somewhere between here and here. Again, our interval is truly containing the population average, even if only barely in this case, right? It is right up next to the edge. Now, 5% of the time, unfortunately, our sample average will be outside of our confidence interval. And therefore, the interval estimate, the confidence interval is the other name for this. The confidence interval that we build will say, we are 95% confident that the population mean is between here and here. And actually, it isn't. It isn't. This is a risk. Specifically, it's 5%. It's quantifiable, which is nice. And so we'll begin to take that idea, confidence intervals and confidence and risk, and we'll explore them next time. So that's all we have time for today. I know we had some questions about homework and stuff, so I'm going to cut the recording as we were out of time, and I'll go back and worry about those administrative sort of details. So I'm going to cut the stream if you're watching on YouTube. Thanks for checking in, and good luck, as always, for both of you. Email me, Discord me if you have any questions, and I'll be hanging around. So